Welcome back to an introduction to Earth Science from the textbook Foundations of Earth Science, the 8th edition by Lutgens and Tarbuck, and brought to you by Pearson Education. We are now on chapter 14, the last chapter on weather and climate, and this chapter is going to deal with weather patterns and severe weather. From here, we're going to begin to talk about our solar system and beyond our solar system. So let's take a look at weather patterns and severe weather. So in this last chapter about weather from our textbook, we are going to learn about air masses, fronts, and the mid-latitude cyclones. So we have to start out with this concept of an air mass and what an air mass is. And essentially, it is just a large body of air that in any direction, horizontally, or actually vertically as well, you have similar properties of temperature and similar properties of moisture. So it could be a very cold and dry air mass, as shown in this particular illustration, or it can be a very warm and moist air mass, or it could even be a cool and moist air mass, or a warm and dry air mass, as you might find over a desert. There's about 5 different air masses, but the bottom line is this air mass is a very large, 1,000 miles across or more, several kilometers thick, so in any direction and with height, an area of air with similar properties of temperature and moisture. And air masses, once they form over their source region, will move, and they're moved by the upper level winds. They're moved by the jet stream winds, and as those air masses move, they affect the weather. It can be warm and, let's say, fairly humid in the southeastern states, but then a very large cold, dry air mass from up in northern Canada can move south under the influence of upper level winds, bring a cold front first, and behind the cold front, that cold, dry air mass, and result in a significant change in the type of weather that we may be experiencing. So an air mass takes on the characteristics of a source region. A source region is essentially a flat region, typically dominated by high pressure with light winds, and that sort of holds the air close to the ground. And that's where an air mass acquires its particular property. So if the source region is the northern parts of Europe, up into areas in northern Russia, flat, cold, tundra, low humidity levels, you're going to get a cold, dry air mass. If it's from an air mass from Antarctica or from the Arctic Circle, you're going to get an Arctic, a very cold, dry air mass. If it's air that's been sitting over the Gulf of Mexico, the Caribbean, Florida, and the Western Atlantic, that air mass is going to end up being a warm and moist air mass. So air masses are classified based on 2 criteria, and it's either going to be cold, very cold, or warm, and then dry or humid. And so cold is going to be polar, very cold is going to be Arctic, and warm is going to be tropical. And then continental, anything that forms over land, is going to be considered dry, and maritime is going to be any air mass that forms over water. And so that results in a humid air mass. So here are your 5 basic types of air masses. Continental, again, refers to dry, and maritime refers to humid. You do not have maritime Arctic. You typically don't have humid air that's Arctic. If it's that cold that it's Arctic, it's going to be dry. So you have continental polar and continental Arctic. So continental polar is cold and dry, and continental Arctic is very cold and very dry. Maritime polar, so that's going to be some cool, humid air on either side of North America, and then maritime tropical, warm and humid air. Those are the 5 air masses, and these are the directions that those 5 air masses generally move with regards to North America. And again, the upper level winds are what will get these winds, these air masses moving, that is. If you have an upper level wind that's digging down like this, it's going to pull this maritime polar air mass down. Maybe you have a ridge of high pressure, so the winds are moving like that. It would pull that warm tropical air up. So 5 basic types of air masses form over the 5 basic types of source regions. And once those air masses form, they begin moving in response to upper level winds. And there's also, didn't mention this continental tropic, very hot and dry. That is a summertime pattern. And as you find that over the southwestern desert, you may also find that over sub-Saharan Africa. In terms of air masses and the type of weather they may bring, continental polar or maritime tropical air masses are very important to North America. North America east of the Rockies is largely influenced, so to the east of the Rockies, largely influenced by continental polar air. That is cold, dry air that slides south from Canada. So it comes in from northern Canada, even the interior of Alaska, and it moves south along the front range of the Rockies, actually uses those Rocky Mountains like a slide, and in the wintertime brings very cold and dry air, and in the summertime brings slightly cool relief to some of the northern states. Other air masses and the weather components in North America, east of the Rockies, is continental polar. We talked about continental polar and its effect on bringing cold, dry air and cool relief. Continental polar can also blow cold, dry air over the Great Lakes in the wintertime. Now, those Great Lakes are warmer than the air. They're not warm like you wouldn't want to go swimming, but they are warmer than the air. And as that cold, dry air blows across the warmer lakes, that cold, dry air picks up moisture from the lakes and dumps it in the form of snow on the leeward side. The windward side is the side the wind comes from, so in this case it'd be from the west side, and on the east shore, that's the leeward shore, and that's where the snow would get dumped. And you can see here that if the wind is coming across Lake Superior from the west and northwest from the very, very cold Canadian polar air mass, as it blows across Lake Superior, it's going to pick up this moisture and then dump it on the lee side of Lake Superior. We see a great deal of that with Lake Erie in and around the Buffalo area, and Lake Ontario in central and northern parts of New York, and there's other areas that see lake effect snow as well. And again, this is a great satellite image of lake effect snow. So here comes that cold, dry air mass. So you don't see anything because it's just cold, dry air, no clouds at all. As that cold, dry air begins to move across the lake itself, that environment becomes unstable because it's warm at the bottom and cold at the top. And remember, warm air rises, so that warm air at the bottom will rise up into that cold air, and that's where you get condensation and cloud formation. And you can see these lines, sometimes they call them cloud streets, that move along with that northwest wind, and you can see them all across the lake. And then as that wind blows across the lake, picks up more and more moisture, it gets to the leeward side, in this case right here, and as that wind blows across the lake, it's moving at a pretty good clip. Once it hits shore, it slows down a little bit. That creates a certain amount of convergence or uplift. That uplift forces precipitation in the form of snowfall, and that is your lake effect snow. Other weather that is derived from air masses in North America, east of the Rockies, your maritime tropical. That, of course, is the air mass that is experienced in the southeastern states and Florida. It comes from the Gulf of Mexico or the Atlantic Ocean, and it is a warm, moist, unstable air mass which brings precipitation. And again, this concept of stability. A moment ago, I talked about the instability of very, very cold air moving in over a warmer, anyway, Great Lake. In this case, it's warm, moist air coming in at the surface, moving north and rising because it is warm and moist, and rising, causing cloud formation and precipitation. One of the things that it's very important to understand with air masses is, of course, first, they form over source regions and they take on the characteristics of the source region. So this continental polar air is forming over a cold, dry, stable source region, and then upper level winds put that air mass on the move. And as that air mass moves from its source region out here to a cool, sort of, let's say, less dry, a little bit more humidity, but still stable, that air mass has been modified. So the important thing to understand is that once air masses form, they do have that stable characteristic of temperature and humidity. But once they begin to move, they will modify. So this continental polar air mass will modify to a less dry continental polar air mass, and then eventually modify to a cool, so polar but moist, unstable air mass, a maritime polar air mass. And even if it continues to go further south, it may actually transition into a tropical polar, or I should say a maritime tropical air mass, a warm and moist air mass. So air masses are these 1,000-mile wide plus regions of air that have similar properties of temperature and density. Fronts are the transition zones between those two air masses. Once an air mass begins to move, the frontal boundary, the cold front, the warm front, it is the transition zone between that air mass and the air mass that it's moving into. So a front is a boundary or a transition zone that separates air masses of different densities. Now, this is very important. I've not talked about density when talking about air masses. I've talked about temperature and humidity. But temperature and humidity are what make up an air mass's density. A warm air mass will be less dense than a cold air mass. A moist air mass will be less dense than a dry air mass. So yes, fronts separate air masses of different temperature and moisture, but specifically they separate air masses of different densities. They separate air masses of different temperature and moisture content, which is a proxy for density. The air masses, as they move along, may retain their identities. The front is the transition zone between that air mass and the next. Now, typically temperature differences do define the front, but sometimes a front simply will separate air masses of different densities, and so I should say different humidities. And so maybe like a stationary front, on one side will be a warm and humid air mass, and then the other side will be a warm and dry air mass. So typically fronts do separate air masses of different temperature, but sometimes they're just simply air masses of different humidity. Fronts, by the way, have both horizontal, so flat against the land extent, but they also have vertical extent. They extend upward, and the front side of that vertical extension is known as the frontal surface or the frontal zone. Something else that's interesting about fronts is that they are also elongated areas of low pressure, sometimes referred to as troughs. Just like a low, the big red L on a weather map, is an area in which winds converge and also air rises. Fronts are also areas, transition zones, along which winds converge and air rises. So fronts are elongated areas of low pressure. They provide lift in the atmosphere. As a matter of fact, they're one of 4 ways to provide lift in the atmosphere. One way is the area of low pressure. The second way is orographically up over a mountain. The third way is thermally, heating up a space, and that air heats up and rises. And the last way is over a front. Air is forced up over fronts because they are zones of low pressure. And fronts are classified as to which type of air mass, cold or warm, is replacing the other. So in a cold front, here, these barbs are pointing in the direction the front is moving. Behind the barbs is cold air, ahead of the barbs is warm air. On the warm front, these half circles are known as pips. The pips are pointing in the direction the air is moving. So the warm front is moving north here, the cold front is moving south, which makes sense. Cold air moving south, warm air moving north. The warm front is moving north, and it's warm air replacing cold air. Stationary front, interchange, back and forth between cold and warm, is a front, the transition zone, that's not moving. And the occluded front is when the cold front actually catches up with the warm front, and we'll show you more of that with the mid-latitude cyclone. So this is the way it looks with a warm front, basically aligned near Kansas City, Kansas, and moving across St. Louis, Indianapolis, Columbus, and Pittsburgh. The warm air is moving in from this direction, all right? The warm air is moving in from this direction, and that warm front is the leading edge of that warm air. Out ahead of that warm front, this air is cool, okay? So you have warm air approaching cool air. Well, warm air is less dense, cool air is more dense. So in this case, the warm air slowly glides up over that cool air. Sometimes this is referred to as overrunning. And as it slowly glides up, of course, uplift causes the warm air to cool until it reaches its dew point, or 100% relative humidity. Further lifting causes condensation, cloud formation, and eventually precipitation. And the situation here is you have warm air over cool air, and that creates a stable environment. So your clouds typically are flat with moderate precipitation, and if that cold air is cold enough, the precipitation is going to fall in the form of snow. So warm air replaces cooler air. As you get closer and closer and closer to the front, you get closer to the point where the warm air meets the cooler air, those clouds are going to be lower, and warm fronts tend to have a slow rate of advance with light to moderate precipitation. Remember, I said that occluded front is when the cold front catches up to the warm front. That's because the warm fronts have a slower rate of advance. A cold front, cold air replaces warm air. They advance faster than a warm front. And oftentimes, because that cold air lifts warm, moist air straight up, they are associated with strong thunderstorms. Violent weather, certainly, but certainly, if nothing violent, at least strong thunderstorms. The intensity of the precipitation is high, but the duration of the precipitation is fairly short. And of course, once the cold front moves on by, that cold air mass moves in with cooler conditions, cooler air sinking, which creates sinking air and drier conditions and clearing conditions. So that frontal zone represents a transition in weather. And this is what our cold front looks like. Basically the same area. Your cold air is moving into warm air. Now that cold air is heavy and sits at the ground, so as it advances, it lifts that warm air and almost straight up. As that warm air is lifted up over the frontal zone, the frontal surface, of course it cools until it reaches its dew point, 100% relative humidity right here, where the lifting creates condensation and cloud formation. But because you have cold air over warm, the warm is at the surface, the cold air is moving, this is an unstable environment. Remember, with the warm front, it was a stable environment. Now you have an unstable environment, and instability tends to produce clouds with vertical extent, like these cumulonimbus clouds, which provide the heavy precipitation in the more active weather pattern. Stationary front essentially, once cold air moving south or warm air moving north, modifies to a point that you don't have a lot of difference over the frontal boundary. Your front becomes stationary, and you're getting your alternating pips and barbs. The flow on both sides of the front is typically parallel. These arrows show them coming straight at each other, but essentially you'd have cold air coming down around high pressure from north to south, warm air coming up on the backside of high pressure, south to north, and this warm air would be flowing north, the cold air would be flowing south, and that transition zone doesn't shift one way or the other. And typically you get light, showery precipitation along a stationary front as well. The occluded front is the situation where our cold front catches up to the warm front. So here you have a warm front moving along, a cold front and moving along slowly, where that warm air is upgliding, overrunning over the cool air. It's being forced up over the cool air. The cold front is marching along much more quickly, more like a bulldozer, bulldozing that air, that warm air straight up. And of course, this is an unstable environment because you have cold air over warm. Here you have warm air over cold. So bottom line is unstable environment, and you have clouds of vertical extent and thunderstorms. Here, more stable environment, you have flat clouds and showery precipitation. All right. Eventually, that cold front catches up to the warm front, and that is your occlusion. All right. Here you have warm air in contact with the ground. There's a difference between warm air and cold air. Now it's all cold air, and all that warm air gets lifted up. And as that warm air gets lifted up, your thunderstorms tend to transition into more stratiform clouds, stable clouds, and showery precipitation. So an active cold front overtakes a warm front. That cold air wedges the warm air upward, and so you start out with thunderstorms and maybe heavy rain, and then eventually your heavy rain sort of transitions into light rain along that occluded front. So putting all this together, we create something that we see across the mid-latitudes, which is the middle latitude or the extratropical cyclone, sometimes called the mid-latitude cyclone. And it's a middle latitude because it's not in the tropics, and it's called extratropical sometimes because, again, it's not in the tropics. It's a cyclone. It's an area of low pressure. Like any area of low pressure, the wind blows counterclockwise and inward into it. But essentially what you've done with this area of low pressure is the counterclockwise and inward flow has pulled cold air mass south and a warm air mass north. And that cold air mass being pulled south, the leading edge of that cold air is going to be your cold front, and your warm air mass being pulled north, the leading edge of your warm air is the warm front. Now, this mid-latitude cyclone is not occluded yet. When this cold front on either side, when the cold front catches up to the warm front, that's when you're going to have the occlusion. And this is the primary weather producer in the mid-latitudes. If you don't have a mid-latitude cyclone moving along, then you have a big area of high pressure, and high pressure creates fair weather. In between big areas of high pressure come cyclones, or areas of low pressure, or mid-latitude cyclones. So the mid-latitude cyclones, they move east. They move eastward, which means they move from west to east. They move from west to east across the United States. And they start up near Canada, and they drop in with the low pressure, and the cold front follows, and the cold front sweeps on by, bringing showers and thunderstorms, and then eventually cooler and drier air. And we even see cold fronts as far south as Florida. Here's an example of what I would refer to as a full latitude cyclone, because it's as big as the entire continent here, but there's our area of low pressure at the surface, your counterclockwise and inward airflow. So the counterclockwise and inward airflow is bringing cold, dry air down behind it, warm, moist air out ahead of it. The cold, dry air, the leading edge of that is the cold front. Okay, here, the cool, dry air is slowed down and is basically stationary along this maritime tropical air mass. All right, here the warm, moist air is moving into the cooler and moister air mass. So here you've got warm, moist air rising up and over, creating stratiform clouds here, maybe light precipitation. perhaps snowfall on the backside of this low, and then along our cold front, you have your thunderstorms. And you can see that also if you draw a line from A to B across this. So look at this continental United States, from A in Iowa to B in New Jersey. Here's A to B. There is the cold front, a little ways downwind of A, and then you got the warm sector. This is known as the warm sector. It's like of this slice of pie, this is the warm sector. And then you have that warm, moist air riding up and over the cool air mass. And here is the occlusion where the cold front has caught up with the warm front. And all around the low now is cold air. And that indicates a weakening low, because lows really derive, or mid-latitude cyclones derive their strength by the difference between the warm air and the cold air. Here, there's warm air in contact with cold air straight across this low. And the difference between those two air masses, a very cold air mass and a very warm air mass, will create a very powerful low. Sort of a cool air mass and a slightly warm air mass will be a much weaker low. Well, that temperature difference that gives this mid-latitude cyclone its energy, once that occlusion occurs and all that cool air is lifted, now you have no temperature difference across the low, and that low is beginning to weaken, and sometimes we refer to that as filling. So if you are up here in Maine, the first thing you're going to see as this mid-latitude cyclone approaches is some clouds, some high clouds moving into your area, all right? And then eventually those high clouds will turn to some light precipitation. Then you may be in the warm sector for a day or so, and then the cold front will move on by with showers and thunderstorms, and then behind the cold front, you'll get that much, much colder air. So the weather associated with fronts we kind of talked about. With the warm front, you have clouds that become lower and thicker the closer you get to the actual warm front, and generally light precipitation. And once that front passes, your winds are going to turn from the south, because again, it's warm air, and your temperatures are going to warm up. With cold front approaching, that cold front lifts that warm, moist air straight up, creating that wall of dark clouds, those thunderstorms. Again, remember, the warm front ends up with warm air over cold in a stable environment, and a cold front, it's cold air over warm in a very unstable environment. That very unstable environment produces those storm clouds that go straight up, and then you get heavy thunderstorms, possibly flaying rain, hail, and occasional tornadoes. And then once the cold front and the storms pass, behind it the northwest winds drive that cool air in, and the temperatures drop. Here is an excellent set of images to sort of help explain that mid-latitude cyclone. Here are our components of the mid-latitude cyclone. There's our area of low pressure, all right, our occluded front extending from the area of low pressure to the point where the cold front is just now catching up to the warm front. The warm front itself extending out, the cold front itself extending out and back, all right. This is going to be known as the warm sector. Right in here is the warm sector. The counterclockwise and inward flow into the low. Back behind it, back over here over California, there's going to be a clockwise and outward flow around the high. All right, that's where that flow is coming from, clockwise and outward, counterclockwise and inward. All right, cold CP, cold, that's polar. C, continental cold. Dry air is being pushed down or moving down into a warm, moist air mass, MT, maritime tropical, warm and moist air mass. The warm and moist air mass is lifting to the north. The cold and dry air mass is lifting to the south. The line from the Red River Valley, Texas, Oklahoma, out into just off the mid-Atlantic from E to A is here, down here at the bottom, E to A, all right? From E to D is the area behind the cold front. In the area behind the cold front, continental polar air is feeding in high pressure. This low is moving in that direction. The low is moving off in that direction toward the northeast, so high pressure is building in behind it. Between E and D, the skies are actually clearing. Northwest winds are bringing in colder, drier air, and the skies are clearing. Along the cold front here, which is right here at D, that is our cold front. If you look down here at the bottom, there's our cold front. Along the cold front, cold, dry air, which is cold and dense, is moving in along. And I've often used the analogy, this is like a bulldozer. It's like a bulldozer. That's a bulldozer blade. There's a big bulldozer back here. There you go. That's my bulldozer. It's the big bulldozer, and it's literally lifting my warm and moist air. And it's as that bulldozer is pushing into the warm and moist air, it's lifting that warm and moist air up. It's lifting it up. And if you look at the image above, here the warm moist air is being lifted up. There the warm moist air is being lifted up. And back behind it, that cold air is coming in. That's the bulldozer coming in. Now, when I said that fronts are elongated areas of low pressure, This is why. The air is coming in from the south and west, from the warm moist air. The cold air is coming in from the north and west. There is convergence. These winds are converging along that frontal boundary. So the convergence helps to provide lift. And then the fact that you have warm air being forced up, when it gets up to this point, that is where it cools to the dew point. When the temperature reaches the dew point, the air is said to be saturated. Further lifting creates condensation, cloud formation. Condensation is a warming process. And now you have cold air that's moving over warm air. It's an unstable environment, and you get your clouds of vertical extent. If those clouds get up to the tropopause, of course, they're going to create an amble top like that. All right? Heavy showery precipitation. Now between D and C, this is the warm sector. That is the warm sector, or like our warm slice of pie. That is the warm sector there. And then this is the southwest flow into our warm front. And here, the southwest flow at this point C to B, that is the warm air. Now it's moving forward. It comes up to that cold air. What is less dense? Warm air or cold air? Warm air is less dense. So it rides up and over. This is the overrunning, or the upglide. It goes up and over. And again, as it's forced up, it cools by expansion until its temperature reaches its dew point right there. Further lifting creates cloud formation and condensation. And if you have enough cold air, you're going to get some snowfall associated with that. All right? Between G and F, that's where the occlusion has occurred, where the cold front's caught up with the warm front, and the cold air has literally lifted all that warm air up. The cold front has come along, and it's caught up to the warm front, and in doing so, all the air that was in the warm sector here has been lifted up. And of course, when warm air is lifted up, it cools by expansion until it reaches its dew point, creating clouds and precipitation. But it's a light and showery precipitation. And if the air is cold enough north of this, then you're very likely to have some snowfall. So you likely find snow north and west of the low, clearing skies behind the cold front, a line of showers and thunderstorms ahead of the cold front, some clouds, those amble tops extending out ahead of the cold front, and then clouds associated with the warm front out ahead of the warm front. And what does that look like? Well, it looks like a big comet in the sky, and quite literally, mid-latitude cyclones do create that comet in the sky. Our low is somewhere in here, all right? Our cold front is going to be probably here. Our warm front is going to extend out like that. And I'm just going to have to use this color to be our occluded front. There's our occlusion right there. So both pips and barbs are on the same side. All right. So here is our warm sector. All right. Here are our southwest, south, and southeast winds. That southerly flow bringing warm, moist air. Warm, moist air. The leading edge of that warm, moist air is that warm front. We'll say north of the warm front, you probably have more of an east, maybe a northeast wind flow bringing in cool, maybe even cool and moist air, right? And then back behind the low, you have a northwest wind bringing in cold and dry air. Oh, look at that, counterclockwise and inward. And back here somewhere, there's a big area of high pressure in which the winds are blowing clockwise and outward, clockwise and outward, clockwise and outward, clockwise and outward. And again, the two are connected together. That's where your air is coming from. Along our cold front, you're going to get thunderstorms here. You're going to get nice thunderstorms here, all right? In this whole area, and out here, you have those thin clouds that thicken up. And then any of this could be rain or snowfall. You probably have your snowfall right up here. And that is your typical mid-latitude cyclone. Once this cold front passes, skies are going to clear and the air is going to get cold. So if I get rid of all that and I just bring this cold front into Florida, here comes a cold front into Florida, right? So as that cold front approaches, the first thing you can see, if you're standing here in Orlando, that's a person, the first thing you can see are the high clouds associated with the anvils. Those are the thunderstorms right there. Those are the thunderstorms along the front, and the anvil clouds come downstream. Then you're going to get the thunderstorms marching down the peninsula, and then behind the thunderstorms, clear skies, and what kind of weather? Cool weather. That's the cool weather we get in Orlando after a cold front passes by. So now we want to talk about how our high pressure at the surface and our low pressure at the surface are affected by the winds aloft. And when we say the winds aloft, we're talking about the winds that happen at the top of the troposphere, right at the tropopause, our upper level winds. Sometimes these are as high as 5,000 meters, between 5,000 and 6,000 meters. 12 to 15, 18,000 feet above the surface. That is our flow aloft. That's where the jet stream lives. That's the core of those stronger winds within these winds. And that jet stream, as you can see, makes these same types of patterns as winds at the surface. We have ridges of high pressure and troughs of low pressure. And those ridges of high pressure aloft, that's a high aloft, and those ridges of low pressure aloft, they also move clockwise and counterclockwise. So how do those motions help to create the vertical motions up and down, downward sinking air, upward rising air, that create high pressure and low pressure at the surface? Remember, low pressure at the surface is when air moves counterclockwise inward. I'm going to use red. Low pressure at the surface is when air moves counterclockwise and inward. It converges on that area of low pressure, also converges on those fronts. And because it converges, it piles up and air rises. Air rises. So air is mechanically being forced to rise by convergence at the surface. But this zone of divergence aloft, this wind flow aloft, also aids in that uplift in the same way as the zone of convergence here in the upper levels aids in that sinking air. Why does that air sink? The air sinks because at high pressure you have sinking air that moves outward and clockwise, outward and clockwise, outward and clockwise. Let's start with a clean palette. And I want to show you how in the upper levels we create these zones of convergence here, all right, and then zones of divergence here. Zones of convergence here above high pressure and zones of divergence here above low pressure. In our zones of convergent, winds are coming together. When those winds enter the entrance region of the trough, if I take this trough and I split it in half, this is the entrance region, okay, say EN, and this is the exit region of the trough on this side, EX. When those winds enter the entrance region of the trough, they are coming together. They are being forced together. It creates a zone of convergence. The air gets squished together. It can't go up to the tropopause, so it goes down. So it goes down. And that is how you get your sinking air at the surface. In the same way with your zone of divergence aloft, these winds are coming through this trough. Now they're in the exit region, and in the exit region, they are spreading apart. They are moving away from each other. There's a zone of divergence here where you're evacuating. Some mass is going in that direction, some mass is going out in that direction, and the evacuation of mass here creates a vacuum, and it can't be replaced from above because it can't be replaced through the tropopause, so it gets replaced from below, and you get air rising up off the surface over low pressure. So around a ridge of high pressure, the entrant zone of your trough creates a zone of convergence and sinking air, creating high pressure aloft. Once you move through your trough and you get in your exit sector, exit region of your trough, divergence aloft pulls air up off the surface. And of course, that sinking air that sinks down to the surface, sinks to the surface, it strikes the surface, it can't go into the surface, so it spreads outward. And which direction? Clockwise. That's right, it turns right because of Coriolis. And this air that's being pulled up off the surface, it's being pulled up off the surface, it causes air to converge on it, and the pressure gradient, the high pressure gradient, causes it to be pulled inward, and it's get pulled inward and clockwise. Inward and, check that, inward and counterclockwise. Inward and counterclockwise. So ultimately, it is these zones of convergence and divergence aloft that create the vertical motions that create high pressure at the surface and low pressure at the surface. And you may be asking yourself, well, what creates these upper level winds? What creates that flow aloft? Well, essentially the flow aloft is created because down to the south, around the equator, it's warm, and up to the north, near the poles, it's cold. Warm air rises, wants to move from the south to the north, from the equator to the poles. It's deflected to the right by Coriolis, and the winds blow in the upper levels around the Earth. And of course, the fact that the Earth's spinning beneath it with mountain ranges and oceans creates these wavy patterns. And these wavy patterns are ultimately created by the differential heating of the Earth, where it's warmer at the equator and colder at the poles. That differential heating, warmer at the equator, cold at the poles, causes air to blow in the upper levels from south to north, get turned to the right by Coriolis, and end up in these wavy patterns. And it's these wavy patterns that create the sinking air to create high pressure at the surface and the rising air to create low pressure at the surface. And again, once our air begins to rise at the surface, right, that counterclockwise flow brings cold air south, right? It brings warm air north. Oops, that's supposed to be a red arrow. Warm air north. Try that again. There's my warm air north. Warm air north, that is the warm sector. The leading edge of that warm air is our cold front. The leading edge of our cold air is the leading edge of the cold air is the cold front. The leading edge of the warm air is the warm front. And really, this whole mid-latitude cyclone was forced by this zone of divergence aloft. That zone of divergence aloft, where wind is moving away from itself, creating an area of divergence, a vacuum, pulling air up off the surface, creates a counterclockwise flow that brings cold air south and warm air north, and creates the mid-latitude cyclone. All right, that should give you an overview of air masses, fronts, the mid-latitude cyclone, and then those vertical wind motions caused by upper level wind flow that creates our highs and our lows. We're going to quickly work our way through thunderstorms, tornadoes, and hurricanes to sort of wrap up this whole section on weather. Thunderstorms oftentimes associated with cold fronts, but also oftentimes associated just with the warm equatorial regions. Those are cumulonimbus clouds, right? Cumuliform, meaning they're high clouds. They have clouds with vertical extent. Nimbus, meaning they have rain. Heavy rainfall, lightning, and occasional hail. You have high occurrence of them, of course, in central Florida. That's no huge surprise. You actually have higher occurrence of thunderstorms in central western Africa, the equatorial region of Africa. And by the way, on any given day, there's about 25,000 thunderstorms that occur. The stages of development in a thunderstorm, many thunderstorms are created in warm, humid air masses, like in central Florida. So you have a hot, humid air mass. Air begins to rise as the day progresses and heats up the land. You start to get cumulus clouds that form, and eventually individual cumulus clouds may gather together in one big updraft and create your cumulonimbus cloud. So warm, moist air rises. As that air rises, remember, this is warm, moist air. It's got heat and humidity. As it rises, rising air is forced to cool until it reaches what point? At the flat cloud here, the flat cloud bottom, its dew point. At that point, the air is saturated, 100% relative humidity. Further lifting creates condensation and cloud formation. But condensation and cloud formation is a warming process. Condensation is a warming process which forces the air to continue to rise, creating your towering cumulonimbus cloud. And this is the stages of your simple air mass thunderstorm. In the cumulus stage, you have an updraft, right? Once you start getting condensation right here, once that warm, moist air at the surface cools by expansion as it rises, cools to the dew point to get saturation or 100% relative humidity. Once condensation begins, condensation releases heat and you get an updraft. And that updraft creates this cumulonimbus cloud. Within the updraft, different processes, one known as the Bursztyn or ice crystal process, another known as collision and coalescence, takes cloud droplets and creates much, much larger raindrops. Cloud droplets are teeny tiny, raindrops are pretty darn big. So collision and coalescence and the ice crystal process take cloud droplets, turn them into raindrops, and as rain begins to fall, it creates a downdraft. So now you have your classic cell, your cellular convection cell, your cell with an updraft and a downdraft. Well, once that downdraft begins, cool, dry air gets pulled in on both sides of the storm. That downdraft causes cool, dry air to be pulled in. That's known as entrainment. And cold air is heavier than warm air, right? Cold air here is heavier than warm air, so it sinks. As that cold air falls to the surface, it strikes the surface and spreads out. The leading edge of that cold air is like a little micro cold front. It's a downdraft and a gust front that spreads out. Have you ever been standing around when there's thunderstorms in the area, then very suddenly you get a cold gust of wind that blows by for a couple seconds? That's that leading edge of that downdraft, that leading edge of that cold air. But as that downdraft moves away from the thunderstorm, it literally chokes off the updraft, and once that updraft is choked off and disappears, the thunderstorm rains itself out. Tornadoes can form from severe thunderstorms. This is an air mass thunderstorm, kind of a typical everyday thunderstorm. When thunderstorms become severe, you don't get the situation where the downdraft chokes off the updraft. Differences in wind speeds and wind directions with height cause this updraft to actually be tilted, and when it's tilted, the rain falls well away from the updraft, and it never chokes it off and allows that storm to become much, much stronger. And those are the types of storms that can produce tornadoes. Tornadoes are very short duration. It's a rotating column of air that extends down from the cumulus cloud, also sometimes defined as a violently rotating column of air in contact with the ground. And it has to be in contact with the ground for it to be a tornado. If it just comes about halfway down, that's a funnel cloud. If it contacts the ground, that is a tornado. A tornado is a cyclone, a counterclockwise spinning in the northern hemisphere with extremely low pressure inside. That extremely low pressure actually cools the air and causes the condensation, which is what causes that cloud to form in the middle of that funnel. The funnel cloud is because of that low pressure and the cooling that low pressure creates. Obviously, very powerful winds. And sometimes you get smaller little vortices, little spin-ups that occur inside of a stronger tornado. And we're going to show you that graphically here in just a couple of seconds. Tornadoes are associated with severe thunderstorms. They are produced from the interaction between thunderstorm updrafts and those upper level winds. And it's a fairly complex process, probably beyond the scope of this class. And you get a whole lot of them every year. Most frequent in the springtime when cold air comes down to meet the warm air. The cold air is here because it's spring, so we just finished winter, and the warm air moves up from the Gulf of Mexico. Warm, humid air comes up to meet the cold air, and those general atmospheric conditions are very good for generating severe thunderstorms, and that's where you get your typical tornadic activity around a severe thunderstorm. A pretty decent number of thunderstorms in Central Florida, but your most frequent thunderstorms here in Tornado Alley. And again, think about the springtime. Warm, moist air is flowing up off the Gulf of Mexico to meet cold, dry air that's still in place from Canada. And the clash of those two air masses, the warm and moist meeting the cold and dry, you get a lot of thunderstorms in this area. And so this is why you have this Tornado Alley area here from about Texas on up almost into the Great Lakes. And again, we talked about the main tornado here, and this is one of those suction vortexes that can sometimes spin around the main tornado. So this is kind of the morphology of the tornado. On any given day, there's a number of different situations that can create air that spins along a horizontal axis. It might be one of those gust fronts from a thunderstorm from maybe even the night before, where you have slightly stronger winds up above and slightly weaker winds below. And that slightly stronger wind above causes air to begin to turn over. That begins to turn over. And these spinning tubes of air, sometimes referred to as zones of baroclinicity, these spinning tubes of air, imagine they're like a rolling pin. You know how you roll out dough, a rolling pin. And they're not very windy. You might not even know they're there. And they exist during the day. Well, as the day progresses and heats up and thunderstorms form, if a thunderstorm forms over one of these spinning tubes of air, it literally, the updraft will pull that spinning tube of air into the vertical, all right? It pulls it into the updraft. Now, that's not the tornado at all. What happens when this occurs, when that spinning tube of air is pulled into the updraft, is the entire thunderstorm, 3 to 10 kilometers across, begins to rotate. The entire thunderstorm begins to rotate. And that rotating thunderstorm, the core of that thunderstorm that's rotating, is known as the mesocyclone, middle-level, middle-sized cyclone. That's the spinning cyclone. Before, when we talked about tornadoes being a product of interaction between thunderstorm updrafts, that's the updraft is the mesocyclone, and tropospheric winds, what happens when this mesocyclone forms, now this is down at the surface maybe 6,000 feet, this is up at the top of the tropopause, maybe 18 to 30 or even higher in the summertime, maybe 40 or 50,000 feet. So you're talking about very strong upper level winds. This mesocyclone becomes so powerful and so violently rotating that when those upper level winds come in from the west and strike that mesocyclone, they're either deflected around it or actually down behind it. And when those upper level tropospheric winds strike the mesocyclone and get deflected down, that creates a little vortice that spins up and gets pulled down as the tornado. It's a fairly complex process. Again, a little bit beyond the scope of this class for now, but it is that mesocyclone. And so if you're ever listening to the news with severe weather going on, they may talk about rotating thunderstorms or rotation. That rotation is this mesocyclone, the spinning updraft of that thunderstorm. So again, the updraft is coming in, maybe from all sides, and the whole updraft is spinning. All right, the whole updraft is spinning. So the whole core of this thunderstorm is like this big, gigantic spinning tube. All right, big, gigantic spinning tube. That is a very, very powerful updraft. And it becomes almost a solid thing. And so those upper tropospheric winds, they're usually typically coming in from the west, maybe at 100, 150 miles per hour. They come in and strike the backside of that mesocyclone, and they either go around it, which is why our anvil top gets that sort of that round shape, and then go out this way, or some of those winds go down. And when they go down, they tend to rotate in the opposite direction. And as they go down, they create what's called the rear flank downdraft. Okay, that's a rear flank downdraft. So this is an updraft, and here's your downdraft. Well, it's the interaction between this downdraft and this updraft where you get a little vortex that spins up, and the downward motion of that vortex is what spins into your tornado. So here's some of the basic characteristics: the speed, how far they can go, their maximum winds, and of course the intensity or the strength of a tornado is based on what's called the Fujita scale. Actually, it's now called the EF scale, which is the enhanced Fujita scale, which has taken in some additional information. But you know, EF0, EF1, EF2, EF3, EF4, and EF5. All right. A tornado watch is a way to alert the public of the possibility of thunderstorms that could produce tornadoes. So a watch, in this case, and a tornado watch, is essentially says the atmosphere is conducive to the development of thunderstorms that could produce tornadoes. That's what a tornado watch is. Tornado warning is issued when there's we actually think there's a tornado. Now that can be one of two things: either the tornado is sighted, all right, or it's indicated by radar. The use of Doppler radar helps to see that mesocyclone. Doppler radar can see the winds coming toward and away from the radar site, and that recognizes the Doppler radar. So radar doesn't actually see the storm itself. It just sees it doesn't see the tornado itself. It just sees the rotating storm. So that's my Doppler radar site. Okay, that's my Doppler radar site. I know it's a great Doppler radar, and it sends out a pulse of radar. And if over here, I'll use this color, I have my thunderstorm with my mesocyclone, my updraft, that's my updraft. This is the bottom of the storm goes up, that's my mesocyclone. So this is spinning in this direction. This Doppler radar allows the radar to see the winds moving toward the radar site and see the winds moving away from the radar site. And when Doppler radar shows very powerful winds, 60, 70, 80, 90, 100, 120 mile per hour winds moving away, and similar speed winds moving toward the radar site in very close proximity, it knows that there's a rotating thunderstorm. It knows that there's a mesocyclone. And so Doppler indicated tornadoes are essentially those tornadoes that are indicated by the Doppler radar. They're not actually seeing the tornado. The tornado is too small of a vortex and too low to the ground. They're seeing the mesocyclone. Doppler radar is actually seeing the mesocyclone. So most tornado warnings are really Doppler indicated. It's being indicated by Doppler radar seeing the mesocyclone. Which takes us now to hurricanes. According to the text, the most violent storms on Earth. Of course, they are also centers of low pressure, just the same way that tornadoes are. They always form over the tropical oceans. Tropical cyclones, which is what a hurricane is, a hurricane, tropical storm, or a tropical depression, they all come under the nomenclature of tropical cyclone. Cyclones in the Indian Ocean, typhoons in the Western Pacific, they are all the same thing, the same storm. They're all tropical cyclones. Tropical cyclones form when the water temperature is about 80 degrees or warmer. So they have to form over the tropical oceans. You need that warm, moist air to give you the energy for the storm. And of course, they are characterized by very intensive convective activities, very powerful updrafts and strong thunderstorms spinning around the center of that circulation. In order to be considered a hurricane, you have to have 74 mile per hour winds. So from 39 to 74, we call those tropical storms. They have a name: Tropical Storm Pat, Cindy, Bill, Franker, Sam. All right, when they reach 74 miles per hour, they become a hurricane and a Category 1 hurricane. There has to be Coriolis in order for hurricanes to begin to spin. So you don't get Coriolis at the equator. You get the maximum Coriolis at the North Pole and the South Pole. So essentially, you have to be far enough away from the equator for there to be spin imparted in these storms. And so typically you see tropical cyclones forming between 5 and 20 degrees north or south latitude. Of course, they can create catastrophic winds and seas, as we have seen in the past and certainly have seen in the last year or so. There's your pretty typical satellite presentation with your banding lines of thunderstorms wrapping into the center of circulation of a very well-defined eye and an eye wall. Most of the intense part of the storm is going to be right there in that eye wall. You have to have warm water, so the central Atlantic in this area is actually fairly cool water. You get some warmer water over here, but you don't really get any tropical cyclones forming in the South Atlantic. These are the tropical cyclones that we're most familiar with in North America. You can also get tropical cyclones developing in the Eastern Pacific, the Western Pacific, where again they're called typhoons, and then in the Indian Ocean, where they're called cyclones. And these red areas are the typical paths of the storms. And of course, what we hope for here in North America is that they're going to recurve and stay out in the middle of the Atlantic Ocean. So here's kind of the cross section of the tropical cyclone, the hurricane. You have your low at the center where the winds converge and rise. The eye of the storm is actually an area where you have a high pressure right here in the middle. And you know it's high pressure because on top of hurricanes, winds actually move pretty calmly, actually, outward and clockwise. So you have this outflow at the top of the hurricane, inflow at the bottom of the hurricane. And so this is a big, gigantic heat engine. The warm, moist air flows in at the surface where convergence, it's low pressure, convergence at the surface, forces it to rise. It rises until it reaches its dew point, or 100% relative humidity. At that point, condensation occurs and cloud formation. And of course, condensation is a heating process which forces the air to rise further. But if you're talking about very warm, moist tropical air, well, that heating process of condensation is magnified, and these updrafts become very, very powerful and very, very strong, creating these very, very powerful thunderstorms and creating the strong winds that blow into the middle of them. So you have your eye wall near the center where you have rising air and intensive convective activity, and that's where you have your greatest wind speeds. And again, at the very center, and talked about this being like a heat engine, the fuel, the warm, moist air is coming in, wrapping into the center, going up, and then the exhaust, just like the exhaust pipes in your car, the exhaust is going to be this outflow aloft. And you have to have the outflow. If you don't have the outflow aloft, if you don't have this high pressure aloft, you're not going to get a good tropical cyclone. So they tend to be very vertically stacked. They go straight up and down. And the outflow aloft is very important, almost as important as the inflow at the surface. Again, as I said, the energy of a hurricane comes from the condensation of water vapor. That latent heat that's released from condensation gives them their energy. So they typically develop with warm, moist air, so basically in late summer. They form in all tropical waters, as I said, except the South Atlantic and the Eastern South Pacific. And as I said, they start out as tropical depressions, which is a closed low with winds up to 38 miles per hour. Then they get a name when they become a tropical storm with winds from 39 to 74 miles per hour. And of course, above 74 miles per hour, they are called hurricanes. What causes a hurricane to diminish? Well, they move over cooler water. And simply because if they're over cooler water, they don't have as much energy. The cooler air, the cooler water has, well, lower temperatures and also less water vapor because it's cooler. Cooler air holds less water vapor. And that means you have less latent heat release from condensation. With less latent heat, you have less of an updraft, which means you have less wind flowing into the updraft, and you have lighter wind. So if hurricanes move over cooler water, they will diminish. They'll also diminish if they move over land for the exact same reasons. They lose that water vapor. They lose that warm, humid air. I talked about the heat engine. This says large scale flow aloft is unfavorable. But what that means is if you don't have that outflow aloft, this is not going to work. If you don't have this outflow aloft, all this air that's rushing up will get here and get stuck, and that'll keep any more air from rushing up. And if air is not rushing up, then air is not rushing in. The only way air can rush in and then up is for it to also be able to go out. And so if the upper level flow does not have high pressure and light winds aloft, you're not going to get a healthy hurricane. So hurricanes weaken or diminish as they move over cooler water, over land, or if the upper level flow becomes too strong and unfavorable. So here are your sea surface temperatures, and again, that 27.8 is kind of the threshold. That's in Celsius, and this is the area where you're typically going to see tropical storm, tropical depression, or hurricane formation. And that's essentially for the Atlantic basin, exactly where we see it. Obviously, hurricanes do a tremendous amount of destruction, really based on the strength of the storm plus the population of the area affected. The shape of the bottom of the ocean has a lot to do with whether there's storm surge or not. And really, you also have to look at the type of population that you're dealing with. If you're in a developing country, construction may not be adequate to deal with a hurricane. Developed countries, you may fare a whole lot better. Just like tornadoes have the enhanced Fujita scale, hurricanes have the Saffir-Simpson scale, and that ranks the relative intensity of the hurricanes. One aspect of hurricanes that you may never have thought of if you haven't lived along the coastline, which is quite impressive, is the storm surge. And the storm surge is where the winds blowing across the water cause water to pile up. And that storm surge can be 15 feet, it can be 30 feet. In a weak storm, maybe only a couple of feet, but a very powerful storm can have 10, 15, 20, 30 foot of storm surge. And what that means is, imagine where the ocean is right now at the beach, if you live by the beach. If storm surge comes up 20 or 30 feet, that means the entire ocean comes up 20 or 30 feet. And then the gigantic waves are on top of that higher level of the ocean. So you add the gigantic waves to the storm surge. One thing to remember when we are looking at the intensity of a hurricane is where you are in the hurricane makes a big difference as to its intensity. This is all being done in kilometers per hour, and I know we're typically accustomed to miles per hour, but we're just going to go with it. So if this is my hurricane, and this is my eye, and it's moving in this direction at 50 kilometers per hour, if we take this hurricane and we cut it into quarters or quadrants, that's not the prettiest lines, but this is the right front quadrant, all right, and this is the left rear quadrant. So the right front quadrant of any hurricane is always going to have the most powerful winds, because you take the actual forward motion of the winds, all right, and then the winds on the right side, which in this case are 175 kilometers per hour, and you add them together to get this net wind of 225. Whereas on the left side, over here in Jacksonville, Florida, you take that wind of 175 and you subtract, because the winds are moving in this direction, but the storm's moving in that direction. You subtract that 50 and you get a net wind of 125. So what you can see is, if you're on the right side of the storm, there can be a significantly more powerful wind than what you're going to see on the left side of the storm. And that's something that's very important when forecasting the potential impact of a tropical cyclone, is that tropical cyclone may have a significantly greater impact if you're on the right side of the storm. Now, one last bit about landfalling tropical cyclones is that in addition to the storm surge and the devastation from rain and wind, they also have the potential to generate tornadoes. As these bands of storms move across the Atlantic Ocean and then strike land, the individual storms within these bands have some interesting things that happen to them as they move from water to land. As they're moving across water, they may be moving at that 150, 175 kilometer per hour rate, but when they hit land, they suddenly have to deal with the force of friction, and that force of friction will slow them down. So what you see are bands of storms that are racing in this direction, but when they hit land, they slow down, and by slowing down, the Coriolis force, the force that's trying to pull them to the left, to the right that is weaker, which means the pressure gradient force, which is trying to pull them to the left, is stronger. And a lot of time what happens is these thunderstorms, as they race on shore because of a drop in Coriolis and an increase in pressure gradient, they turn to the left. They'll turn left into the center of the storm, and the entire storm will begin rotating because of it. Because it's the winds at the surface that deal with the friction. The winds aloft are still blowing in the same direction. So the winds at the surface may be coming in here, and they should have an arc like that. But in reality, they come in and they turn like this. But the winds aloft are still moving in this direction. They're still moving that direction. And so that creates a turning in the storm. Well, if you recall from our tornadoes, our rotating thunderstorms are the type of storms that are far more likely to generate tornadoes. And therefore, landfalling hurricanes or rain bands associated with hurricanes or tropical storms near land oftentimes do, in fact, generate tornadoes. Last but not least, something you've probably seen a lot of over the years, and certainly in media. You can find this at the National Hurricane Center website as well. And this is just your basic 5-day track of a storm. And what the 5-day track tells us is that when we look at modeling or forecasting of hurricanes or any weather feature, we know that today we probably have a pretty good idea of where it will be in 12 hours. And this first location is 12 hours. The margin of error is pretty narrow, all right? Not a huge margin of error. So this cone means the center might be right here where we forecast it, or as far to the right as here, or to the far or the right left is there. As you go out in time, 24, 36, 48 hours, now that margin of error has grown. Pretty typical with a weather forecast, which means that center might be right here on the forecast, but it could be as far to the right as here, or the far to the right as here. Then you go out 72, 96, 120 hours. Now you have a very broad potential margin of error. That center of the storm can be anywhere along that line from way over here to the middle to way over there. So when you're looking at the cone with a hurricane forecast, please remember that what that cone's telling you is the center of that hurricane could be anywhere in that cone during that time frame. That was Chapter 14 from Foundations of Earth Science, the 8th edition, written by Lutgens and Tarbuck and brought to you by Pearson Education. Of course, we were wrapping up our section on the weather and climate with weather patterns and severe weather. Next, we're going to leave planet Earth and go into our solar system, and then from our solar system, we're going to look beyond into the universe from Foundations of Earth Science, the 8th edition.